This section covers the topic of probability. Probability is really a ratio of essentially, I like to think, what you want to have happen out of the total number of options available. We have specific events that we want to happen, like we might want to roll doubles, or we might want to get a full house or something along those lines. So those are events. Outcomes, slightly different, would be all of the possible things that could happen. But because we're looking at a ratio, probabilities are always between 0 and 1. Anytime there's an impossible event, you have a 0 probability, and anytime there's an event that is absolutely guaranteed to happen, that's when you have a 1 probability. Discussions about probability almost always start with rolling a single die, right? So that's a number cube that has 1 through 6 on it. So we're going to write each event in set notation, and then we're going to give the probability that the event is going to happen. So the number showing is a multiple of 3. So our event, E sub 1, in set notation, what are the available values that are multiples of 3? Well, we could have a 3, or we could have a 6. So then, what's the probability of that happening? We write the probability of event 1 will be 2 out of 6 total options, which we always reduce to 1/3. Event 2, the number showing is less than 6. Okay, well again, we can write that in set notation. Our possibilities are 1, 2, that's a terrible 2, let me try that again. 3, 4, 5, oops, and that's it. So then what's the probability of event 2 happening? Well, it's 5 out of 6 total possibilities. Event number 3 is that the number showing is 0. So how many ways can that happen? Well, it can't happen at all. So this is one of those impossible events. So the probability of event 3 happening is 0. And then event 4 is that the number showing is greater than 0. So again, we can list out each possibility. Well, it could be a 1, or a 2, or a 3, or a 4, or a 5, or a 6, which means the probability of event 4 is 6 out of 6, which gives it a probability of 1. You are guaranteed to have a number showing on a die greater than 0. The sample space are all of the possible outcomes that can occur. So when we talk about the outcomes in the sample space that actually don't belong to the event, we call that the complement of the event, and we write that E prime. So, for example, when they talk about drawing a single card from a standard deck of 52, E might be the card is an ace. Well, there are 4 aces in the deck, so that would be 4 out of 52. Then E prime would be the event the card is not an ace. So obviously that would be the difference. We write it like this. When you combine the event and its complement, you get your whole sample space. When you take those things, so this intersection means the things they have in common, they have nothing in common. You could think of it also with this rectangle. So this is my whole sample space. My event fits in here in this red part. The complement is everything that doesn't fit into that red part. So we'll try a problem on complements. In the experiment of drawing a card from a well-shuffled deck, find the probabilities of event E, the card is a heart, and of event B, E prime. So if we look at the probability of E, meaning the card is a heart, well, I've got 13 heart cards out of 52 total. And that gives me a probability of 1/4. The complement would then be Everything that's not a heart would be the remaining 39 cards out of 52 total, which gives us a probability of 3/4. So if you add together the probability of your event and the probability of its complement, you should get a value of 1.
Do you notice the driver?
Now I know you're all familiar with the phrase, may the odds be ever in your favor. So how do odds differentiate from probability? Well, truthfully, odds are the same kind of idea, but instead of expressing the probability of some event out of the total number of options, the odds actually represent the probability of an event compared to its complement. So, for example, if the probability of rain can be established as a third, then the odds would be 1/3 rain to 2/3 no rain. That's the difference. So you would have 1/3 over 2/3, or essentially a 1 to 2 odds that it will rain. So that's really the difference is, again, rather than saying 1 out of 3 chances, you're saying 1 to 2 odds. 1 chance it'll happen, 2 chances it won't happen. So the next problem, we're drawing a marble at random from a bowl that contains 6 green, 4 blue, and 8 yellow. Find the odds in favor of a yellow. So what we want to know is how many yellow to the amount of not yellow. Well, there are 8 yellow. There are 10 not yellow. So we would say that we have 8 to 10 odds, or we would reduce that as 4 to 5 odds. 4 times it'll happen, 5 times it won't happen. Now here's where the notation can get a little bit mucky. We're going to use set notation to represent probabilities. And this first notation we're going to use is the union of 2 sets. So when you think about a union, many of you will get married and you'll have your box of CDs and your wife will have her box of CDs, and since you guys both have a Justin Bieber CD, you'll get rid of one of them. So a union is when you take everything from one set and everything from the other set and get rid of anything that overlaps. So if we have these 2 probabilities, probability event H is we're going to get result is a 3 when we roll a die. And for K, the event is an even number. So here's H, here's K. When we put them together, this is what we see. So the probability of H is 1 out of 6. The probability of K is 1/2. And when we put them together, we end up with 4/6 or 2/3. So we've added these together. Before you assume that this is true in general, you have to consider another event G. And event G is the result is a 2. So now we're going to look at the probability of G and K. So G's result is a 2, so we have 1/6. For K, we have an even number, again is a 1/2. When we take the union of these, we've got 2, 4, and 6, which is a 1/2, because we had to take out this overlap here of 2. We don't need to show that twice. So we always remove that piece. So the notation here would say you take the probability of G plus the probability of K, but it cannot be the probability of the union of the 2. So here's some common examples that can be shown. So here's event H, here's event K, there's event G where it overlaps. H and K can't occur simultaneously because K is even numbers, H is 3. So that's called mutually exclusive. They cannot occur at the same time. K and G can occur at the same time because we've got this 2 that overlaps them. So K and G are not mutually exclusive events. And one thing that's always true for mutually exclusive events is that there is no intersection between them, right? These will never ever overlap. So when we're looking at the probability of the union of 2 events, we're looking at the probability of event E happening or event F happening. So we're looking at the union. What we have to do is take the probability of each event and add them together, but you subtract out the place where they overlap. And that's always going to occur when you're looking at event E or event F happening. So let's look at a couple of examples. Again, we're drawing a single card from a well-shuffled deck of 52. So what's the probability that we have a red card or a king? So that's what I'm looking for, the probability of red or king. Well, half the cards in the deck are red. So the probability of getting a red is 26 out of 52. And there's one king in each suit. So that's going to be 4 out of 52. Now, for the purposes of what we're doing, I'm not going to reduce these fractions. The probability of having a red king, well, there are 2 of those. So when we're looking at our total probability, we need to take 26 out of 52 plus 4 out of 52, and then we subtract those 2 that are red kings, because we can't count those twice. And we get 28 out of 52, which can be reduced to 7/13. The next one, what's the probability that the card is a club or a diamond? So the probability of a club, there are 13 of those. The probability of a diamond, again, there are 13. Can you have a club that's also a diamond? You can't. So what we'll have to do is just add our 2 probabilities. 13 plus 13 gives us 26 50-seconds, which we reduce to a half. So you have a 50% chance of selecting a card that is either a club or a diamond. Now we start rolling 2 dice, the sample space changes, and that's what I've got down here, and you should also have it in your notes, because we can have a 1 and a 1, a 1 and a 2, a 1 and a 3, and a 1 and a 2 might not be the same as a 2 and a 1. So just kind of keep that in mind as we look through these. So find the probability that the first die shows a 5, or the sum of the 2 dice is 11. Well, the sum of 2 dice being 11, that's easy. They're listed right here. There's 2 of them. Now, how about the first one being a 5? Well, that's this row right here. So easy enough, we can just look at this. 5, 6, 7. So we've got a 7 out of 36 probability. The way that we would add this together, the first die showing a 5, that would be 6 out of 36. The sum of 2 dice being 11, that would be 2 out of 36. And we subtract the one that overlaps. Taking a look at the next one, the sum of the dots showing is at least 9. Please pay attention. At least means it can be more than 9. So where do we have 9? Well, here's 9. And then all of these. So if you just look at the sample space, you can count them. You have 10 out of 36. Some probability notation that you need to be familiar with, or some properties of probability. First of all, probabilities will always be between 0 and 1. They can be equal to 0, they can be equal to 1. If you have an event that is absolutely guaranteed to happen, I'm going to roll a die and I'm going to get a number larger than 0. That is a certain event. The probability of an impossible event is always equal to 0. The probability of rolling a single die and getting a 7 is 0. When you're looking at the complement, you always take 1 minus the probability of your event, or the idea that if you add the probability of event and the probability of its complement, you will get 1. And so finally, if you're looking at the probability of event E or F happening, what you're looking for is the union, which means you take the probability of the first event plus the probability of the second event, and you subtract out all those Justin Bieber CDs that you have in common. Next, we're going to look at a binomial experiment. This is where we're going to start running an experiment, and we're going to have independent trials with only 2 outcomes. The most common form of this is flipping a coin, because your outcome is heads or tail, success or failure. So let the probability of success in one trial be P. The probability of failure is 1 minus P, because it's its complement. And the probability of exactly R number of successes in N trials is shown with this formula. So, in order to look at binomial distributions in experiments, I'm actually going to show you some calculator steps first, because I see no reason for you to have to calculate all of this by hand. So first of all, think of we're rolling a single die 10 times. And what we want to find the probability of is that in exactly 4 rolls, our result is a 3. So you need to have some numbers written in first. First of all, you have to know that the probability of getting a 3 is 1/6. Your N value is 10, because that's how many times you're actually conducting the experiment. You're rolling 10 times. And then your R value is 4, meaning that that is the exact number of rolls that we're looking for. So in order to do this on your calculator, you're going to go to second and then vars. And you're going to scroll down to the one that says binomial PDF. There it is, it's number 0. The first number that you're going to enter is your N, number 10. Then you have to put in a comma. The next thing you're going to enter is your probability, so in this case it's 1/6. We're going to keep that in parentheses, and then another comma. And then the last number you're going to enter is the R number, the exact number of rolls that you're looking for. Close your parentheses. And that's going to give you your probability. We're going to use those same steps that we learned to actually run the next probability. So we're rolling a die 12 times. We want to know that in exactly 3 rolls, the result is a 5. So the probability of getting a 5 is 1/6. N is the number of times that we're rolling, which is 12. And R would be exactly how many tries we're looking for. It's 3. So that's what I'm going to put into my calculator. So just to show you what needs to go in, you're going to go to binomial PDF. You'll first put in your N. You'll put in your probability. And then you'll put in your R. And when you do that, you'll find the probability is approximately 0.197. Let's try the next one. The probability that in exactly 8 of the rolls, the result is not a 5. So the probability of not a 5 is 5/6. We're still rolling 12 times, but now we're taking 8 rolls to get not a 5. So what I'll put in rolls, my probability of 5/6, and the fact that I get to use 8 rolls to do this. And when I hit enter, I get that the probability is approximately 0.089. You can represent probabilities as percents. So this one would be about 19.7%. This one would be about 8.9%.